Hello everyone. Can you hear me?
Yes, sir.
Yeah, awesome. Okay, so how was your weekend? Did Was it productive? Were you sleeping all day? Did you try any questions? How did it go? चल रही है जिंदगी. लॉकडाउन में बर्बाद हो गए. Yeah, man. Lockdown is emotionally, yeah. And अच्छा वहाँ तो गर्मी भी है ना. Yeah, that is right. And what do you guys do for like pastime? Like, do you play do you play Ludo? Do you play on Netflix? Okay. Dmux binge. Who does that? Hmm. PUBG. Nice. Good, good. In US, everyone hates Trump, or it is just media hypes. Mm, the video is recording and it might go public, so I cannot say anything. तुम तो मोदी fan. And टेक्स्ट कर दे. हाँ, पर्सनली मैं कर दूंगा. Okay, so last time, whatever questions we discussed, did you guys try to implement it? Did you face any issues? Was it okay? How did it go? Do you want any discussion around those questions, or should we move to the next topic? Next topic? Okay. So, like, I would say that whatever topics, like whatever algorithms which are covered so far, those are the primary algorithms: BFS, DFS, Dijkstra's, topological sort. Most of the graph questions you can do using just those algorithms. Today we'll talk about spanning trees. So we'll talk about minimum spanning trees and how to find those minimum spanning trees using two algorithms, Kruskal's algorithms and Prim's algorithms. And you won't find any question on this in interviews, like most probably. So during my Microsoft interview, I had one question on Prim's algorithm, but it was because I had worked on Prim algorithms and it was like in my CV somewhere. So the interviewer saw it and asked, "Okay, do you know Prim's algorithm? Can you code it?" But other than that, I haven't seen any question which uses Prim's or Kruskal's algorithm. So yeah, the moral of the story is also keep open eyes on your CV. Um, you can get questions if you have something in your CV which you don't know. Either prepare for it before the interview, or um, yeah, you might face difficult time. Okay, so let us start with minimum spanning trees. I hope the whiteboard is visible.
Yes, sir.
Sir, algorithms project में कैसे काम आती है? Yeah, so the Prim's algorithm which I'm talking about, this I used in image segmentation project. There was one project on image segmentation, and there actually we were segregating like different components in an image, and that problem we reduced to minimum spanning tree basically. So that is why we used Prim's algorithm there. Um, Straight away I don't know whether they are useful in today's world or not, but like who knows, you might use them sometime. Okay, so today we'll talk about minimum spanning tree. And let's first see what spanning tree means, then we'll just qualify it as minimum. Okay, we'll use some term and we'll call it as minimum. So what is tree? What do you guys know about tree? Is it a graph first of all? Can I call a tree a graph? Yes. Yes. And yeah, so someone says connected acyclic graph. That is right. So it is a connected acyclic graph. So what does connected mean? Connected means that you can go from one node to the other, like from any node to the any other node. So there exists a path between every node. So path between every pair of nodes. Okay, that is connected. What is acyclic? Acyclic means there are no cycles. So somebody is asking, isn't it a DAG? So trees, whenever we are talking about, those are like, first of all, like DAG could be a tree, but not all DAGs are trees. Can you give me an example of? There is one more property actually. So if there are n nodes in the tree, how many edges should this graph have? N minus 1. So tree is a graph with n nodes having n minus 1 edges, and it is connected. So the sufficient information is to have this red things, n nodes, n minus 1 edges, and connected. So if you have these three things, it will automatically imply that it is acyclic. You can prove it, or you can read the proof online somewhere. It's not important for our case. It's just that if you have these three things, you can prove that it is acyclic. So you just need these three red circles, and that is the definition of a tree. Okay, now we understand what tree is. uh, what does spanning mean? Can anybody guess what does spanning mean here? So what is the literal meaning of spanning? Spanning means covering something, right? Right. So spanning means, so we are trying to create a tree out of a graph. That is the idea. So you're given a graph G and you want to create uh, a tree from it. That is the idea. And the graph itself has a set of vertices and a set of edges, right? So those define the graph. Now, what we are saying is, when we are saying the tree is spanning the graph, that means vertices of G is vertices of T. So the tree will contain all the vertices of the graph. It will contain a smaller subset of edges of the graph. So E of T will be a subset of E of G. So vertex set is equal, edge set is a smaller subset such that it becomes a tree, right? So if graph has n nodes, spanning tree will have the same n nodes, and it will have smaller number of edges. How many edges will be there? There will be n minus 1 edges. Is that clear? And what does minimum mean now? So if the graph is weighted, you would want to find a tree whose cost is minimum cost tree. And what is the cost of a tree? The cost of a tree is sum of edge weights. So let's take an example and see what does this mean. So we want to find a tree whose sum of edge weights is minimum. So I'll give you one example and let's see if we can find the minimum spanning tree. So okay, let's take this. Now I'll just label the nodes A, B, C, D, E, and let us give some edge weights. Okay, let us say this is 1, this is 2, this is 3, this is 8, this is 4, 3 again, and 1. Okay, so yeah, this is the given graph. Now what would be the uh, minimum spanning tree for this weighted graph? So T, which is, you want to find minimum spanning tree, MST. Okay, so MST will have, what will be the vertices in the tree? The vertices will be same as the graph. So I'll just draw all the vertices. So A, B, C, D, E, and you will pick edges such that the cost of the tree is minimum. So let me just draw one of the trees and then let's see if that is the minimum spanning tree. So I'll just pick this edge, this edge, this edge, and this edge. Okay, so 1, 2, 1, 4. So how many nodes are there? There are 5 nodes. And how many edges are there? There are 5 minus 1, 4 edges. So that is our tree. And what is the cost of this tree? So the cost is 4 plus 2, 6, and 2, 7, 2, 8. So the cost is 8. That is one of our options. Let's draw one more and let's see whether there are other possibilities of a spanning tree. So it will have all the nodes A, B, C, D, E, and let me just pick a random set of edges. Okay, let's pick this, 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 and this. So 3, 1, 4, and 8. And what will be the cost of this? The cost of this will be 16, right? Now, as you can see, a graph can have many spanning trees. So 1 is a spanning tree, 2 is also a spanning tree, and there can be more possibilities, right? But 1 is the tree with minimum cost. So that is the only minimum spanning tree. Can there be multiple minimum spanning trees? So there could be multiple spanning trees. Okay, the question is, can there be multiple minimum spanning trees? So we just saw that there could be multiple spanning trees, but can there be multiple minimum spanning trees? Do you want to take a guess, or? Yeah, right. Because let's take a simple example. So if I change the weight of all the edges to 1, then any tree which I form with this graph will be a minimum spanning tree because all the edge weights are same, right? So I'll have multiple minimum spanning trees. So there could be multiple spanning trees, there could be multiple minimum spanning trees. And the idea is to find one of those. Okay, is that clear? Yes. So if you understand the meaning of minimum spanning tree, and if you can, okay, let us do one more example maybe. And you guys should answer what will be the minimum spanning tree there. So the graph is, let's take, yeah, let's take 5 nodes. Yeah, so this is the graph, and then I'll give some edge weights. And let me label the vertices A, B, C, D, E. Now, can you tell me, can anybody find and help me with the minimum spanning tree? And let's draw that here. Oh, AE is left. Okay. AE would be, let's say 3. So AE, so vertices I'll draw for you because that is the easier part. So Utsav says 2, 3, 4, 6 is minimum. And Rishabh says 14th is the path sum. Let's see. Yeah, 2, 3, 4, 5 actually. So I can take this edge, can take this edge, that is good, this edge, and this edge. So basically here I was able to pick all the smallest. So if I arrange the edge weights in increasing order, I picked all the smallest ones, 2, 3, 4, 5, and I was able to get a tree. So definitely that's a minimum spanning tree. So 2, 3, 4, 5. And what is the cost of this? Cost of this is 14, right? So that completes the example. Now let's start with the Kruskal's algorithm. So if you have any doubts, just stop me. Otherwise, I'll move to the algorithm. So Kruskal's algorithm is like very simple to understand. So what this says is, so first of all, this is a greedy algorithm. And like each iteration of this algorithm involves two steps. So there are two steps in it. The first step is pick the edge with minimum weight. And second is add this edge to the current structure if it does not add a cycle. If it does not add a cycle. So what this means is we are basically trying to create the minimum spanning tree. And how will we do that? So we have all the vertices initially of the tree. Okay, so this will be all the vertices. And then we will successively add edges to this. So we will add edges in every iteration. So how will we add edges? So we'll pick the edge with minimum weight in the graph. Okay, so let's say I picked some edge and I'll add that edge to this structure only if adding that edge in this structure does not create a cycle. Okay, so let's understand this through an example. So I have example written here. Where did clear whiteboard go? Yes, so example. Okay, A, B, C, D, E. And let me label all the edge weights. I'll give some random weights, 2, 3, let's say 1, 2, 3, 4, 6. Is there any other edge remaining? So these two are done. Okay, this one is remaining. That let's take 4. Okay, so this diagonal is 6, this is 3, this is 3 again, this is 2, 4, 4, 2 and 1. Okay, all of them are done. And we want to find the minimum spanning tree, and we'll use Kruskal's algorithm now. So what does Kruskal's algorithm say? So it says to add the vertices, the edges successively. So initially our structure will be like there are all the vertices. So a minimum spanning tree will have all the vertices, but initially there are no edges. Now it says pick the edge with smallest edge weight. Okay, so which one is that? So that is A to E. Okay, so and what does it say? Add that edge to the structure only if it doesn't create a cycle. Okay, so if I add that edge to our structure, will it create a cycle? No, right? So if I add this edge, there is no cycle, so I can safely add this. So this is done. Now again I'll do the same thing. I'll pick the next smallest edge. So there are two options here, AB or ED. You can pick any of those. Let's go with AB. And if I add that edge here, will it create a cycle? No, it won't. So I will add that edge. What is the next? Next is ED. So can I add that edge? Yes, because it won't create a cycle. Next is this 3, EC or BC. Let's go with BC. And will it create a cycle if I add that? No, it won't. So I can take that edge. The next is CE or EC, whatever you call it. That is, so if I add that edge, it will create a cycle. So this will be the cycle. So I can't use that edge. So I'll put a cross. Then I'll move to next smaller edge. So that is 4. If I add that, that will also create a cycle. So I can't add that. Then I will go for CD. Adding that will also create a cycle. So I won't add that. By the way, have I already created a tree? Yes, right? So any edge, if I add now, will create a cycle. So how many times should I run this algorithm? Should I check for all the edges or should I stop somewhere? Yeah, so I should run this algorithm for n minus 1 additions, right? So while you make n minus 1 additions to this structure, you should run this algorithm. And will it take n minus 1 iterations or it can take more? So it can take more iterations, right? So it will take n minus 1, like at least n minus 1 iterations. And why can it take more iterations? Because the edges in the middle can form a cycle, right? Yeah. So at least n minus 1 iterations, and we'll have to run it for n minus 1 additions of edges. So is that clear? So I shouldn't have even gone for CE because I have got 4 edges, like n minus 1 here is 4, right? So any edge which I add now will basically create a cycle. So I already got a tree here. So let me change the example a little bit. So A, B, C, D, and E, and let's see. So, assigning some edge weights 1, 2, 1, 2, 3, 2, 4, 3. Okay, so these are the edge weights. Now, can some of you, like one of you, unmute yourself and tell me how do I apply the Kruskal's algorithm here? If you understand, can you help me here? So this is my A, B, C, D, E. And let's use the Kruskal's algorithm to get a minimum tree. So anyone? Pick AE. Is somebody speaking or should I just go ahead? Okay, the smallest one now is AE. So I'll pick that and I can add that to this structure because it won't create a cycle. So I get AE. What next? So this is done.
AB.
AB.
So next will be BE, right? Because the edge weight is 1. So I will check whether BE creates a cycle in this structure. So it won't create a cycle. So I add that edge here. So this is done. What next?
BC.
Yeah, I can add BC, but let me also check for AB, right? Because that is also weight 2. So I check for AB, it will create a cycle. So I won't add that edge. Okay, so I'll put a cross. Then I move to BC. Can I add that edge here? Yes, I can add. So that is 2. And then can I, what is the next edge? So BD is the next edge with edge weight 2. Can I add that? Yes, I can add that. So should I check any other edges or I'm done? Done, right? Because I have already added 4 edges. Okay, so that completes the Kruskal's algorithm. Now, if you understand that, we'll talk about the implementation, but what is the crucial thing in implementation? What is the missing piece? What is the thing which we don't know so far? Yeah, checking cycle, right? So in each iteration, what are the 2 steps which you are making? So the 2 steps which you're making is first to pick a minimum edge with minimum edge weight. So pick edge with minimum edge weight. And the next step is to check if this creates a cycle. Or let me write it more concisely. So basically add it if it doesn't create a cycle. Right? So we can pick the minimum edge. Maybe we can sort the edges in some form and we can use some data structure. That seems easy. The question here is how can I check cycle successively, like in each iteration after adding edges? So do you have any ideas what will be the naive algorithm for this?
Sir, for each node we can check for cycle. No, it will not be naive actually. We can just pick any node and apply BFS over it. But थोड़ा मॉडिफिकेशन करके होगा सर कि BF उस नोड के बाद उसके पेरेंट को भी पुश कर दें और जब मैं 2 से पॉप करूं तो मैं 2 चीजें पॉप करूंगा, एक पेरेंट नोड और उसका पेरेंट, क्योंकि मेरे को विजिटेड एरे में अगर विजिटेड सेट में अगर मेरे को एक्सपेक्ट करना होगा कि मैं उस नोड वापस मतलब वो उसका नेबर है कि नहीं, तो पेरेंट भी आ रहा होगा, इसलिए मैं पेरेंट को भी डाल रहा हूँ क्यू में.
Yes, so if, like, let's say if this was the graph and you are running BFS, so when you start from this node,
Yes, sir.
you will add all of these children in the queue, right?
Yes, sir.
And you will mark this as visited.
Sir.
But when you come at this particular child, you will have this as the neighbor, right?
Sir.
How will you know if this is the same edge or if this is some like new edge with a cycle?
तो जब भी मैं किसी भी नोड के नेबर्स को ऐड कर रहा हूँगा तो मैं उसके पेरेंट को भी पुश कर दूंगा क्यू के अंदर, मतलब फॉर के लिए करूंगा तो फिर 2 चीजें पुश करूंगा, ये वाला नोड इसका नेबर पुश करूंगा और फिर ये फिर सेकंड नेबर एंड देन अगेन थर्ड नेबर देन अगेन.
Okay, I see. So I'm just thinking that whether it will work. So if this is the cycle and you start from here, so basically you will push these 2 in the queue, and along with that you will also push this, right, in a pair.
Yes, sir.
And then what will you do? How will you detect cycle here?
सर जब इन दोनों नोड को डाल रहा हूँगा तो पेरेंट को भी डाल दूंगा, और फिर जब ये थर्ड वाला नोड आ रहा होगा तो वो विजिटेड के अंदर होगा, और ये जो जब बी वाले नोड को डाल रहा हूँगा तो ए को भी डाल चुका हूँगा, और जब सी को डाल रहा हूँगा तब दोबारा वापस से ए को डाल चुका हूँगा। फिर जब सी को जब मैं प्रोसेस कर रहा हूँगा तो मैं सी इज ऑलरेडी विजिटेड हो चुका होगा। फिर जब डी को प्रोसेस कर रहा हूँगा तो सी मेरा विजिटेड के अंदर आ जाएगा, तो साइकिल डिटेक्ट हो जाएगी।
I see what you're saying. So basically you're saying कि every child should have the same, like one parent,
Yes,
something
sir.
of that sort.
Yes, sir.
Yeah, so that holds in a tree, and tree is a cyclic. That makes sense. But will it work in every case? So every child should have one parent. Oh, trying to find any counter example to it. And how? Okay. To BFS. Okay. So what about? No, you can't have that. And something like this. No, but you're saying that it will. This might work. Yeah, what you're saying. I'll have to check it, but yeah, it seems it will work. So what will be the time complexity of that?
O of n only. मतलब yes, O of v plus e only.
Right. So if you do that, like it will be, yeah, so that's the naive algorithm basically. So it will take a lot of time, right? So we want something which is faster, through which we can detect cycle in every iteration. I'll think about this. Looks correct, but yeah, I'll have to think more. Yashasvi, we can have a visited array, and then for every new edge, if both nodes are visited, then don't add it. We can have a visited array. And if for both nodes we have visited. Okay, and what does Utsav say? When you add an edge, do DFS. Okay, so that is for cycle checking. You can do with DF, like some modifications to DFS and BFS. Yashasvi has some proposal that we should have a visited array, and then for each new edge, if both the nodes are visited, we shouldn't add it. Is that correct? Visited, and if both nodes are visited. Okay, so what about this? So A, B, C, D, okay. All of them are visited now according to a visited array. But I will have to still add the BC edge to make it a tree. So I cannot use the visited array, right? Yashasvi. So visited array won't work. I mean, you see the counter example here, right? So checking the cycle, which we do here is like we use a particular, like a specific concept. So that what do we do specifically there is, so let's visit the concept first and then I can tell you how to implement it. So basically if there are two trees, so there is tree 1 and there is tree 2. So this is some tree, okay, here. And there is some other tree here. Now if I connect, make an edge from this tree to this tree, like any node, you can make edge from any node to the other node. Will it create a cycle or will it still be a tree? It will still be a tree, right? Because there are like, let's say M1 nodes, and how many edges will be there? M1 minus 1. And here there are M2 nodes, how many edges will be there? M2 minus 1. So when I add this edge, how many nodes will be there? M1 plus M2. And how many edges will be there? M1 plus M2 minus 2 because of these minus ones, and plus 1 because of the new addition. So total number of edges will be M1 plus M2 minus 1. Okay, so if you see, it will still be a tree. Like for M1 plus M2 nodes, there will be M1 plus M2 minus 1 edges. And this is connected because you can visit from every node in T1 to every other node in T2, and like same thing from every node to T2 to every node in T1, and within the tree itself also you can visit any nodes. So this is a connected graph with M1 plus M2 nodes and then M1 plus M2 minus 1 edges. So that is the definition of tree. So adding an edge between trees will always create another tree, right? But that is the first thing to realize. What is the second thing to realize? So the second thing to realize is, if I have this single tree, okay, some tree, some graph, random, and if I connect any two nodes within that tree, so if I connect these two nodes, so they will always form a cycle. So there will be a cycle in a tree if you connect two nodes in a tree. And how can you prove that? That connecting two nodes within a tree will create a cycle? Does anybody have any ideas? Let me read the chat. So we have some. So back edge, it will create two distinct paths between nodes. Yeah. So basically, where did my pen go? Yeah. So basically, oh, mm, yeah. So basically, if I connect A and B, uh, So if I connect A and B, what will happen is there was already a path from A to B, right? And then you added this one edge. So basically there are these two paths, P1 which is a direct edge and P2 which is the other indirect path. So this creates a cycle. Basically you can go from A to B and take this back edge to create a cycle. So that is the cycle. Okay, so we have seen two things. Connecting two trees won't create a cycle, but connecting any two nodes within a tree will create a cycle. So we use that concept to like iteratively check whether um, adding an edge will create a tree or not. So in Kruskal's algorithm, if you think about it carefully, we are maintaining a forest at every point of time. So what is a forest? So forest is a collection of trees. So my structure initially is all nodes are like one node trees, right? So this is a forest of n nodes or n trees basically, right? And when I add an edge, let's say I add this edge, so this becomes a single tree now. So then it becomes n minus 1 trees. And what is the idea? The idea is you can connect two different trees, but you cannot add edge to single tree. To same tree or single tree, right? So do you get this? That the structure which we are maintaining in the Kruskal's algorithm, that is a forest, and forest is a collection of trees. And what I'm saying is you can connect any two trees that will still maintain a tree, but within a tree you cannot add edges. So question for you is, so this is my T1, right? And this is T2, this is T3, and so on. This is Tn minus 1. So there are n minus 1 trees right now. So can I add this edge? Yes, right? Because this is the edge across two trees. Now this whole becomes one tree. I mean, excluding this node. And can I add this edge now? No, right? Because I cannot add edge within a tree. So that's the high level idea. So is that clear? Are there any confusions here?
Sir, can you repeat what you said at the last?
Yes. So what I was saying is, first thing is, can you appreciate the fact that whatever structure which we are creating, that is a forest. It's a set of trees basically, right? There are some trees T1, T2, up to Tk. And whenever you add a new edge, you can add edge here, 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 or like between any tree to any other tree. That will still maintain the tree structure, but you cannot add edge within a tree. So you cannot add an edge here. So that will be wrong. You cannot add edge here. That will be wrong. And so on for every tree. So the idea is you have to just check whether the edge connects two trees or it connects nodes within the same tree. So if the new edge which you have picked, if it connects the nodes within the same tree, that you won't add that edge. If it connects nodes between trees which are different, you can add that edge. So does that make sense? You can add this edge and you cannot add this edge.
Yes,
Okay.
sir.
Okay. So how to maintain trees in code? Yeah, so we'll talk about code now, how to implement this. This all seems very complicated, right? So we had these two steps. First was to pick an edge, and the other one was to check if there's a cycle, right? And accordingly add or not add, right? So picking an edge is okay. Cycle, we just discussed the high level idea, how to check a cycle, and adding is still fine. I mean, now the thing remaining is like, how do we implement this checking cycle thing and work with so many trees and so on, right? So a simple representation of a tree is like a parent array, right? So basically what you say is, I for every node, so let's say this is node 1, this is node 2, up to node n. So this is the nth node. You will store the parent of that node here. So let's say if parent of 1 is 3, you will store 3 here. Parent of 2 is, let's say, 1, so you will store 1 here. Parent of 3 is n, so you will store n here. Parent of k is, let's say there is no parent of k, that is the root, so you will store k here, right? So let's take a simple example. So let's say this is the tree, 1 2 3 4 5 6. So what will the parent array here? So the idea of parent array is every node has single parent in a tree. So when you were like learning about trees, like you might have already been told that this is one of the representations of the tree, that every node has single parent and that you can represent in a parent array. Okay, so what are the parents for each of this? Can anybody tell me? So I'll write for 6, so it will be 3. For 5 it will be 2. For 4 it will be 1. For 3 it will be 1. For 2 it will be 1. And what about 1? It doesn't have a parent, so we will just put 1 there, right? Yeah.
Sir,
So
what we
through
want
this,
to check? Sir, what we want to check here? Like, why we are writing all this?
so this is the representation of a tree basically. And how will we use this to check the cycle? I'll tell that next.
Okay.
So this is the representation of the tree. So we have this tree structures, right? And basically we want a representation of that, and we are saying, okay, we'll use the parent array for that representation. Okay. So if that is clear, now quickly tell me, okay, let me give you one more example and then you can probably tell me. So these are the two trees, T1 and T2. I'll just label the nodes 1, 2, 3, 4, 5, 6. Okay, and I'll write the parent array for you. One, two, three, 4, 5, and 6. Parent of 1 is 1, 2 is 2, 3 is 2, 4 is 1, 5 is 1, 6 is 3. So this is your parent array. Now somebody gives you the edge and asks you, okay, can I add the edge to 6? Now using the parent array, can you answer that question? So you just know this parent array and somebody asks you, okay, can we add the edge to 6? How would you answer that question using the parent array? Yeah, so Utsav, yeah, that's right. So basically what you will do is you will find the root of both the nodes. So what is like both the trees in which these nodes belong to. So finding root is the key. So what will be the root for node 6? The root will be 2, right? And what will be the root for node 2? It will again be 2. So if roots of the two nodes are same, then that means they belong to the same tree and you cannot add that edge. So if someone asks you whether you can add to 6 edge, you will say, okay, let me find the roots, and then you will see, okay, roots of both of them are same, and then you can answer, no, you cannot add the edge. Now, since you cannot add the edge, you get another proposal and somebody asks you, okay, can I add 3 to 5? So what will you do? You will say, okay, let me see if they are in different trees. To check that, you will say, okay, let me find the roots. When you find the roots, you will see that the root of 3 is 2. And when you find the root of 5, you will find that it is 1. And you will say, okay, those are not equal. They belong to different trees. Then that means I can add that edge. Okay. So basically adding the edge is finding the roots of these trees and checking whether they are equal or not. If they are equal, then you can't add that edge because they belong to the same tree. Otherwise, you can add the edge because they belong to different trees. Now the question comes, how can I find the roots given the parent array? How can I find the root of, let's say, 6 given this parent array? Finding root of 2 and 6, if they are unequal, we can add it. And yeah, so how can we find the root of 6 here? So we have to move up the tree, right? So we will repeatedly move up. How do we move up? We'll move up with the parent pointer. What is the parent of 6? The parent of 6 is 3, which we
3.
get from here.
And then we go to parent of 3, right?
Yeah, then we go to parent of 3. So when will we stop?
Till parent
Till-
and pointer are equal.
Yeah, so till the parent and the node itself are equal. So that is the definition of root, right? If you see here, 2 is equals to 2 and that is the root, and 1 is equals to 1. So that is the another root of, so that is T1's root. So roots have this definition that I is equals to like I, parent of I. So I equals parent of I. That is the definition of root. So you will move up till you get this, right? So you start from 6, you move to 3. From 3, you move to 2. And finally, that is the root. And similarly for 5, from 5, you directly move to 1. And then you got the root, and that is all. Okay, so now do you understand like how to check cycles and all? So for checking cycles, we have this tree structures. The tree structures are maintained in this parent array. in parent array, I'll check these roots and then I can answer whether I can add a edge or not. Okay, so that is one part. How to represent adding an edge in parent array? Yeah, that is the next thing. So once you answered, okay, yes, I can add this edge. What should you do now? What should you do next? How should you modify this parent array? So basically what we are trying to do here is, let me think how to tell it concisely. Yeah, so if you want to add an edge here, 3 to 5, what you will do basically is you will connect the roots. And so the idea is we are not really concerned about like real connectivity, like direct. If I want to add this edge, I'm not really concerned about adding this edge particularly. I'm just concerned about connectivity. So the idea is, so I have these two components, like two trees, T1 and T2. And when I can add edge between like two nodes of this graph, like A and B, I'll just add an edge between the roots, so that I'm not really adding the real edge. I'm just adding this edge for connectivity. So I'm just maintaining connectivity throughout. So the idea is to just keep track of connectivity. So if adding an edge will create a cycle to this structure or not. That's a like little bit takes some time to digest. Like, why am I not adding the real edge? I'm just adding another edge which maintains the same connectivity. And I'm adding that edge to write simple code. I mean, if I add the real edge, it will be really like messy. So the idea is to keep track of connectivity. And for adding an edge between A to B, I will add edge between root of A to root of B. So in terms of connectivity, adding edge AB is same as adding edge between root A and root B. So you can still go from any node to any other node. That's the idea. And because this is a simple operation to code than this one, so this will make many changes in the parent array. We generally do this. How do we account for weights if we are not adding the actual edge? So weights, actually we will just add the weights. So this is basically some other edge. This may not be the real edge, but weights. So when you can add this AB edge, I'll just keep track of, okay, I just added AB edge with weight W1. So this will be my like answer vector, where I will just keep track of all the edges which I added. That won't go into the real structure. I mean, the structure is maintaining something else. It's just maintaining the connectivity. The actual answer you will have to store in some other vector. Okay, so you have learned an important concept here, other than Kruskal's algorithm, that is, so this kind of data structure, parent array, finding root, this is called union find data structure. Okay, so I will show you the code. If I recap everything what we just discussed in Kruskal's algorithm is, there are two steps. First is picking the edge with minimum weight and then checking whether you can add that edge. Now checking whether you can add that edge involves checking the cycle, and checking the cycle only relates to the connectivity, not adding the actual edge. And since it relates to the connectivity, we just do this operation, connecting the roots. Okay. And based on the structure or on the parent array, you can just say whether you can add an edge or not. So that is the overall idea. And if that is clear, we can see the code. If that is confusing, you can just yeah, if you have any confusion, just ask me the questions. I can try to answer them. Yeah, so union find, the data structure which we are using here, this parent array, that, and so we will use methods over this parent array. So those are called union find algorithm or union find data structure. So the find method here is finding the roots. So that is the find method. So when you find the root, that is the find. Okay. And when you add an edge actually, so when you have an answer yes, and then you add this edge. So what is the addition? The addition is root of A connected to root of B, that is union. So you're merging two things. That is one operation. The other operation is finding the roots. That is why it's called union find. And what will be the change when we do the union? The change will be simple. Like when you are connecting nodes, like roots of two trees. So let's say this is tree 1 and this is tree 2. What will you do? Basically, you will just connect this and you will say, okay, parent of this particular thing is now this. So this again becomes a rooted tree. So you will make one of them as parent. So I will make parent of A is B basically. So that will be the change here. So union involves just changing one entry in the parent array, and find involves finding the root from the parent array. That's the union find thing. Make sense? Awesome. So did I leave anybody behind? Is there any confusion or questions? Okay, let's see the code then, if we understand this. So Kruskal.cpp. Okay, so let me share. Yeah, so is my Sublime text visible to you all? Awesome. So this is my Kruskal's algorithm. And so basically I'm given a list which contains the edge weight. So the first entry is the edge weight, and the second entry is pair of like source and destination. So edge has two vertices, and those two vertices are in this pair. So that is the list which I have, and I want to find the minimum spanning tree. So basically, and I'm assuming that this list is sorted, and if it is not, you can just sort it before using it in the algorithm. Okay, so I will iterate. I'll iterate for these edges. Okay, and so this is my. I just get the two vertices x and y and the edge weight. So this is the source, this is the destination, and this is the edge weight. Right now, what I check, if root of x is root of y, if they are not equal, I can add this edge, and then I call this union thing, right? Now, what is the root operation? The root operation is basically the same thing, like go up till id of x is not equal to id of x. So till you get root, and what will happen at root? At root, id of x will be same as x, right? So this is your find operation basically. And once you found the root of the two nodes x and y, if they are unequal, you can add the edge, and that edge is added through union operation. And what does union operation do? Union operation connects the two roots. So first it will find the two roots, and then it will like connect one to the other. It will call like parent of one is the parent of other. Does this sound right? And basically you can keep adding the cost. So minimum cost, you can return the minimum cost of the spanning tree. If you want the edges, you can keep a list of edges. So basically what you can do is you can keep a vector of pair intent. So that will be your added edges. And what would you do here? You will just added edges will be make pair source comma destination. Added edges dot push back. Okay. So finally you will have minimum cost here, and the edges you can like have in this vector. Does that make sense? And how would you initialize this ID or parent array? The initialization of ID array will be all of them are parents of themselves. So ID of I is I, right? So somewhere here I might be calling the initialize. I don't know. Maybe I should. Yeah, so call initialize here somewhere. So initially all the nodes are parents of themselves, and then for successive edges you just try to add. And can I make some more modification to this algorithm? So instead of this for loop, I can write a while loop here, and while I can do additions not equal to n minus 1, right? I can remove this, and I can call variable additions, which is initialized to 0. and I add here additions plus plus. Okay. Yeah, I'll share this code.
Sir, in that case, X and Y won't work, right? X, Y, and cost.
Why?
Sir, P of I is there.
Oh yeah, so you can also keep I, and you can increment it every time. Okay. Yeah, thank you for that correction.
Hello, sir. Sir, could you repeat that whole
Yeah.
I was struck up?
Sorry, say that again. I don't
Uh,
understand.
Could you repeat the code again? I was struck at the beginning.
Okay. So we are given a list of edges, and this list is in this particular form that the first element is the edge weight, and the second element is a pair containing the source and destination of the edge, right? And we are asked to find the minimum spanning tree for the graph with this list of edges. So basically, what we do is, okay, we said we'll do n minus 1 edge additions. So I'm keeping this additions integer, and I'm just checking whether I've done n minus 1 additions. Okay, so that's my while loop. And then I go to each edge. So P of I is one of the edges, and this gives me the source, edge source, and this gives me the edge destination, and this gives me the cost. So I have these three things. Now I need to check if I can add this edge to the current structure. So how do I do that? I just check if the roots are unequal. So that's what I do here. If those are unequal, I do a union operation, right? And basically I just add the cost also, and then I add this edge in my list. Those are the things which you can take care of. The two important operations are root and union. So what is the finding root operation? The finding root operation is moving up in the tree till you find the root. So how do you do that? So you can write a while loop, or you can also write a recursive function. Basically, the termination condition would be when id of x is equals to x. So that will be the root, right? And id of x becomes this. So I just keep iterating on this.
Sir, in this root function, sir,
Mhm.
this x is equal to id of x. Shouldn't it be above line 15?
Mm, x equals id of x. Okay, so let me see. So I'm given a particular index x, and id of x. Actually, I shouldn't even do this at all. X equals id of x. Yeah, this is the only thing I should do, right?
Sir, I think you will have to include that line, but it should be below this line.
So what will that line do?
Sir, if we do x is equal to id of x, so that means that,
Right.
sir, so that means that we will have only single iteration within the while loop, right? No, sir, I get it. Yes, sir, actually, x is equal to id of x would work. Only
Yeah,
that's it.
yeah. So maybe this is not required. and this is the only
Sir,
thing
can
which
you
we,
explain with a small example?
yeah, so the here the idea is basically you're going to the parent, right? Now to go to the parent, parent of x is id of x, right? So this now basically becomes the parent. X is now its parent, and you want to go till parent of x is x. That is the
Yes,
idea.
got it.
Yeah. Yeah, so this I copied the code from last year's some lecture. So maybe that was wrong. You just need to do this. X is equals to id of x. And in union, what will you do? In union, you will just find the two roots and you will make parent of P is parent of Q. Just that, connecting the two trees.
Sir, we can also do vice versa, right?
Yeah, you can do reverse as well. So it's just about connectivity, and even if you do like id of Q is equals to id of P, that is also fine. Yeah, this will also work.
Sir, is there a way to optimize or to identify that the branch does not, sir, the height does not go far more?
Yeah, so this union operation or the root operation, this both involves the height of the tree, right? And you want to make sure that it is balanced so that you have like good running time. Yeah, so there are ways to do that. And there's a small tutorial which I can share with you guys. That's not required, but if you're interested, you can read that. Like I won't even expect anybody to ask Kruskal's algorithm in any interview, because you can see how like it's easy to code, but the idea behind is like little bit involved. There are a lot of things going on in the back end. So not a very good option for interviews, I would say. But still, I mean, since it is easy to code and once you understand the concept, it's like very easy to follow. So you should know. So is this algorithm clear? Are there any doubts? And for optimization, I can share a small post. Like if you're interested, read that. If you're not, just you can skip that. So Kushagra asks, won't it terminate after one iteration? Why would it terminate after one iteration? Okay, cool. Awesome. So that completes our
Sir,
Kruskal's.
like why we are checking
Yeah.
there's an edge between root A and root B every time. Like why we are not checking for those elements itself?
Hmm. Which line are you talking about?
Like uh, i- you explain on whiteboard, right? Like
Right.
we for finding edge between A and we will go for add we will add edge between root A and root B.
Roots. Right. So
Like
the idea there is because this adding edges between roots is easy as compared to adding edges between like in between nodes, because you can imagine like how that tree will change. It won't become a rooted tree. There might be like bad cases. So the argument there is the connectivity still remains the same. Like you can go from any node of one tree to any other node of the other tree. So the idea of adding edge is like creating the same connectivity. So we are not concerned about the actual edge additions, but just about the connectivity which is like brought through that edge. So you could add edge between any node from tree 1 to tree 2 to have the same connectivity. And we are making a particular choice to add edge between the roots. So that's the idea.
So for any nodes, at last we will get to the source node of both the trees. Is it like that?
So we add edge between the roots, and the tree which you get is not the actual tree, like the minimum spanning tree in Kruskal's algorithm. So we are not concerned about the parent array at the end. So whatever edges which we are adding, we are storing them in a separate vector here to
Okay.
keep track of the tree. Yeah. So that is just like one subroutine to check cycle. And how do I check cycle with successive like edges, addition of edges. And the idea there is just to keep track of connectivity, and to keep track of connectivity, just connecting the roots is okay, because that essentially keeps the same connectivity between the two trees. So is there any other doubt regarding that?
Sir, actually, sir, I have one doubt in that root code which was written.
Mm-hmm.
Sir, in that code earlier it was written, sir, in that it would find us the root in half number of operations. If we do this, then it will require, so let's say if this code requires 10 operations, then that code would do the same thing in 5 operations.
So I don't remember what was that line. Let me control Z.
Sir, it was id of x is equal to id of x.
But why are we changing this ID of X?
Sir, we are jumping by 2 positions rather than 1 position.
I mean, we are also assigning this particular element, right? We shouldn't do that. We can only change X, not the array. Like the array ID should be read only in this function. So maybe this should be X equals ID of X.
Yes, sir. This is one and the same thing, right?
Yeah. No. So if you do ID of X equals to this, you're assigning this thing. You're assigning ID of X to something.
Okay.
That will also work. That is some optimization, but like there is another thing which I'll have to explain, which I'm skipping right now.
Okay. Sir, so this code will work correctly?
Yes, yeah, this will work.
Sir, wouldn't it change the value of ID of X?
So the idea here is, again, there is one optimization that you're only concerned about the root. You're not
Yes,
concerned
sir.
about.
Sir, I think that if the values change, we are only concerned that whether the root is same or not. So if the
Yeah.
values change, the root we will get the same.
Yeah, so like this is a optimization. Like you were saying that it should be balanced tree, right? Like to have that optimization. So this is that optimization basically, which will
Okay,
reduce the running time.
sir, so we will reach the root more quickly in this case, right? Because we are remembering
Right,
the parents.
right. Basically, you're remembering grandparent, and every time you're like going up. So once you have reached the grandparent, you're storing it. Okay, this is my ancestor, some ancestor. So this is storing some ancestor. So yeah, this is the optimization, but not required really. You can just do this X equals ID of X.
Okay.
Like this is easy to understand x equals id of x. Once you're really concerned about the implementation running time, you can do like id of x. Yeah, you can do this. Okay.
So in this id equal to id of x, the more like if we put another id of x, we'll reach even faster, right? So like we can do it.
Yeah, you can keep doing it. Yeah. So basically, this will create a logarithmic complexity if you do this. So I'll share that post maybe if you guys want to read. But I would rather say like practice more questions than going through this kind of like weird optimizations.
Sir, I think doing that twice won't benefit because, sir, when we are starting, so at the starting, our parent is that, sir, like each node is the root itself, right?
Yeah, in the starting, each node is the root itself.
Yes, sir. Then what happens is that we increase sir, we add a single child. So we increase the height maximum by 1.
Right.
In each step, we increase the height maximum by 1. And this optimization is decreasing the height by 1 in each step. So at every step, we increase the height by 1. This optimization will decrease the height by 1. So it will maintain the direct route itself. No need to consider parents in between. So this will take care of that situation. So even if we add one more time, then it won't give us an additional benefit. This is the most optimum thing that we can do.
So like when you're doing this union operation and the,
Sir,
let's say if, yeah,
yes, sir. Sir, so in
the,
union, the height will be increased maximum by 1, right? Because all are root.
no, so you can connect two trees, right?
Sir, but the node parent is pointing directly to the root.
Right.
Sir, so it is pointing directly to the root, and we are doing root parent is some other root. So
Right.
in that way, if we consider, then in union we are increasing height maximum by 1.
In union, we are increasing height maximum by 1.
Sir,
Okay.
because we jump to the root and then that root again jumps to the other root. So
Right.
sir, and the above condition, which optimization which we have written, it will decrease it by 1. So once it goes into this thing, it will update that height to height 1. So it will again make,
Right.
sir, so it will again make it optimum.
Right. So once it goes through that path, it will make everybody in that path like point to root again.
Yes, sir. Yes, sir. That is what I mean to try to say.
Hmm. Yes. Yeah. Maybe I should try running a small like example with this and see whether that happens. It feels it's right. But yeah, should try with a small example. Yeah, what you're saying makes sense to me. Okay, so everyone is happy. Any other doubts? Or should we move to Prim's algorithm? Okay, let's move on. Where did my whiteboard go? Any question on this algo? Let's finish the prims first, and then we can do some 1 or 2 question maybe on minimum spanning tree. Whiteboard. So Prim's algorithm is very simple. If you already know Dijkstra's algorithm. So Prim's algorithm, so similar to Dijkstra's algorithm, it will have 2 sets, unprocessed and processed. And initially, so this will be processed and unprocessed. So initially the unprocessed set will have all the nodes from 1, and in each iteration we will move like 1 node from unprocessed to processed. So that's the idea. And how do we do that? So basically whatever we have in process nodes on the process side and whatever we have on the unprocessed side, we consider all the cross edges and we pick the minimum. In Dijkstra's we were picking a minimum path. Here we pick the minimum edge. Basically, that's the difference. So you pick the minimum edge, take that node to the process side, and do that repeatedly for till all get all the nodes on the process side, and you have the spanning tree basically. Then, okay, very simple algorithm, and let's see with an example. So good old example, A, B, C, D, E, and let's add edge weights 2, 3, 2, 4, 5, 2 again, 3, 4. Okay, so these are my this is my graph with these edge weights, and let me draw the process and unprocessed sets. Process set, unprocessed set, and you have A, B, C, D, E all on this side. Now, to begin with, you'll have to pick the minimum edge to move it from one side to the other. Okay, so I pick this minimum edge with weight CD. Okay, so C goes here. And so basically, this will be my minimum edge weight. This is weight 1. And I pick this, then D moves to this side, and I have CD. Or you can directly start with putting C and D in the process set itself. That's the minimum edge basically. That can be the initialization. So let me press edge. Let's remove D also. Now what is from the process side to the unprocessed side? So edges from C. What are those edges? C to B and C to E. So C to B is weight 2, C to E is weight 4, and D to C, okay, that is done. D to B is weight 5, and D to, what else is remaining? D to E. D to E is weight 3. So that is 3. So which one will I pick? I'll pick the smaller one with edge weight 2, and I'll bring B on this side. Okay. So let me is this. So what will be my process set now? So it will contain 3 vertices, C, D, and B. This is 2, this is 1. Now what are the cross edges? The only remaining vertices are A and E. Cross edges from B will be to A and to E both, okay. So this will be 3, this will be 2. Cross edges from C, there will be an edge from C to E with edge weight 4, and there will be a D to E with edge weight 3. Okay, so minimum of this is this 2. So I'll pick that edge and I'll move it to the process side. And how will my, okay, so I need more space here. So how will my process and process sets change? So I will have C, B, D, and now B to E. Okay, the only vertex remaining here is A. And what are the vertices to that, and what are the edges to that? The edges to that are, the cross edges are A to B and A to E. So these are the 2 cross edges. And what are the weights? The weights are A to B is 3, A to E is 2. So basically you will pick this edge and move the vertex to that. And finally you will have a tree. So this will be the new edge. Okay, so is the algorithm clear? Is the example clear? What are we doing here? So basically you are considering all the cross edges at any point of time and you are picking the minimum. That's all for Prince. So in what you're doing here in Prince algorithm is, okay, एक बार repeat please, example. Okay, so this was our graph, given graph. So initially I basically put the minimum edge in the process set, and the 2 vertices, corresponding 2 vertices are C and D. Okay, now I consider all the cross edges. So the purple ones are the cross edges, and I'll pick the minimum of this cross edge. So 2 is the minimum and it is connected to B. So now I move B to the process side. So B comes to the process side, and basically this is my process side, and then I consider all the cross edges again. So new cross edges will be added from B, right? So the purple ones are all the cross edges, and then again and pick the minimum. The minimum is 2, which is connected to E. So E comes on the process side, so you can see E here. And the only vertex remaining on the unprocessed side is A. And there are two cross edges from B to A and E to A. The minimum of them is this AB or sorry, AE edge or E edge. And you use this edge and move like A to the process side. So yeah, the resulting, so if I write all the weights here, you will get the resulting minimum spanning tree. So it will be 1, and then you got 2, then BE was again 2, and AE was again 2. So basically you picked these 4 edges, 1, 2, 3, and 4. These 4 edges, and you got the MSP. Let me color those edges. So this was 1 edge, 2nd, 3rd, 4th, right? So this was your tree. Is it clear? What's the difference between Prim's and Kruskal's? What's the difference? I mean, there's the only similarity between them is they're finding the same, like they are solving the same problem of finding the minimum spanning tree. But the way they are solving is entirely different, right? Cycle will not exist in Prim because why won't cycle exist in Prim? Can anybody give an argument for that?
Basically, so we are taking every node, incoming node, and incoming edge for every node only once.
Right. So basically you already have a tree here, right? And to this tree, you are adding a new node and a new edge. So if you have some tree and you add a new node here and a new edge, you basically for cycle, you need to have more edges. And if you add a new node and a new edge, it's the equation will still hold. So let's say if you had m nodes and m minus 1 edges, adding 1 to both of this will still have the same thing, like m plus 1 nodes and m edges, so that it will still remain a tree. So is that clear? Awesome. So today we talked about primarily 3 things. Minimum spanning trees. In that we talked about Kruskal's and Prim's algorithms. And we also studied about union find data structure, right? You know now what the union find data structure and algorithm there is. So there can be separate questions on union find itself. So what is the time? Oh, it's already 11 for me. So I have like meeting already started, so I have to jump to that. But yeah, today we discussed the algorithms. Tomorrow we can do 1 or 2 questions on this, and then we can conclude graph with the final theory. Whatever is remaining, we can finish tomorrow, and that will be all for graphs. Other than that, I would suggest you to practice a lot of questions from whatever source you want to do. Lead code should be good. It will have like most of the questions. But if you have finished all of those, you can like go for harder ones on Spoj or Codeforces, whatever you like. So that is all for today. And I'm running late for the other meeting. Aren't the remaining topics for graphs not necessary? Yeah, they are not important for interviews. Yeah, not really important. What are the remaining topics? So the remaining topics are Tarjan's algorithm. I have never to teach Tarjan's algorithm. I'll also have to read it again. I don't remember it. I've never used it. So what else is remaining?
Sir, Bellman-Ford and Floyd-Warshall for negative edge weights.
So Bellman-Ford is not asked. Floyd-Warshall is a good algorithm, I would say. Yeah, Floyd-Warshall we can study. That you might use. Bellman-Ford, I have never seen anybody, but yeah, we can see what can we cover tomorrow. Because tomorrow is the last class for graphs. I'll plan it accordingly. If you have any other questions for Carson. Yes, yeah, there are many graph algorithms actually, but not many of them are important. Like I would say Prince and Kruskal's are also not important, but they're just good to know because they're taught in CS courses. But let me see what can we cover tomorrow and what will be more important for interviews. And then we can go from there. Does that sound good? Or if you guys want, you can vote among yourselves and just let me know what topics you want for tomorrow. Tomorrow's class. Okay, so I have to go to another meeting, and if I get late, it won't be very good. So I'll see you guys tomorrow. Bye-bye. Have a good night. Stop share.